right, so here we go on number one on this problem set. And in our y, we want to make sure that we show that we understand why this happens in the universe. So we got this athlete training, and we have a position versus time graph. So the position for something to have in here right away, let's see. The position time graph shows his location. What is it? And the other understanding, let's see what they ask us. Let's see what they ask us about. They ask us about velocity. They ask us about a lot about velocity. So, how is the velocity related to the position time graph? Thoughts? How is the velocity related to the position time graph? Going back to chapter 2. Velocity change. What does velocity describe? Direction, speed. And another way to put that is that it describes the way the position is changing. What on a graph shows the rate something's changing? You know, what on the graph? What on a graph? Just a general graph. The slope. So, things that I would expect in your y would be like velocity is the rate the position changes. And therefore, the slope of the position time graph is the velocity. Those are the key points that if I was reading your y for this problem, that I would look for. That it shows its location, that velocity is the rate the position changes, and that therefore the slope of the position time graph is the velocity. Those are your key understandings that you need to have to understand this problem. Okay, so I think what would be useful here is to probably have our graph. So let's grab our graph here. All right. So I'm going to grab my paper copy here. All right. So for A, let's see. For each segment of the graph, find the magnitude and direction of the athlete's velocity. And we know from our y that velocity is related to the slope. So we're looking at segment A here, which is from 0 to 60 meters and the first 10 seconds. How do I find slope? Rise over run. So in general, slope is rise over run. And I can even write, since I know the slope is the velocity, what's my rise? Which type of quantity is on the y-axis here of this graph? meters, which is a measure of distance to displacement, right? So that's actually my delta D. And what's on the x-axis? Time. So that'd be delta T. Oh, wait a minute. I've seen that before. That's my definition of velocity. Right? Because remember, velocity and displacement can both be a vector. That line over it indicates, hey, this is a vector, so make sure you take into account what direction. It's a half arrow. Yeah, it's a half arrow. All right, so for part A here, let's see. The slope, which is the velocity. My rise is from 0 to 60, so that's 60 minus 0. My run is from 0 to 10, so that's 10 minus 0. This is meters and meters and seconds, which is 6.00 meters per second. Well, remember that we have delta D here, and rise is a change. Anytime you have a change, delta is final minus initial. So looking back to this, for my rise, which is my delta D, my final is 60, my initial is 0. And then 0. Yeah. Because that would be incorrect. I don't go from 60 down to 0. I go from 0 up to 60. And change is always final minus initial. If you started the day with $60 and you ended the day with 10, how much did your money change? Okay? And it becomes really important with the positive and negative ideas. Yep. Not each point, each segment right now. That's what it's asking for. See, for each segment of the graph, find the magnitude and direction of the athlete's velocity. So the fact that this came out positive tells us what direction is the athlete moving in. The positive direction. So the direction here, we could call it like positive X. Or we could even just draw an arrow and say that way. Yes? Okay, take a second with your table and try B. See what you come up with. Going over B. So this was A. Now let's go over B. Same idea. That the velocity is going to be the slope. And my rise over my run. My rise here is, 0 meters. My run is 30 seconds minus 10 seconds, which gives me 0.00 meters per second. Certainly. No, because it's a horizontal line, it has a 0 slope. But straight line just means the slope isn't changing. Yeah, because I'm looking for the change in time. And the change in time, it started at 10 seconds and went to 30. So that's 30 seconds minus 10 seconds. Why would I what? Because it asked me for segment B, what's the average velocity? Just because that's what they wanted to do. I conform to their wishes. Oh, that's all right. We've done BA, we're still on part A. Sorry, I thought each one they labeled A, B, C, D. Does that make more sense then? Okay. What's the direction? Is it going positive or is it going negative? Okay. Why positive? Right. It's not positive. They're not moving. That's what I would put. No direction. In the X direction, because the only reason I put that is because they labeled this as X. So they're saying, hey, we're going to define down the track as the X direction. Negative X. They've said, let's call the direction down the track X. We could have just as easily called it Y, D, T. But they chose X, so I was just staying with their notation. But I actually like this better, the arrow. I think it's, or you could say down the track. Certainly. Well, the bottom is going to come out to 20 seconds, and 0 divided by 20 is 0. Yep. But it's important that I still do the bottom because therefore I confirm that I should have it in meters per second. My top, even though it's 0, is 0 meters. Let's try C. Let's do it together. So for segment C, on BC here, what's my change in displacement? What do I end up at? For my displacement? My displacement is on the y-axis. So I end up at 40 meters. Where do I start? I start at 60 meters, yep. And what time does that segment end at? It looks like 45 seconds to me. And what time did it start at? 30 seconds. So on the top, I get negative 20 meters. And on the bottom, I get 15 seconds. Which, let's see, that's negative 1.33 meters per second. Oh, it's negative. So which way was the athlete moving? Backwards. So far, if I'm looking at this motion, they ran down the track for 60 meters, stopped, and then started running backwards. I think it wasn't a race, it was just training. It's kind of weird to do in a race. And then we have our last one to do, BD. And let's look, let's see. I end up at 100 meters. Ooh. Looking at it, do I expect a positive or negative slope? Positive. And it's good to get those things in your mind, because then when your answer comes out, if it comes out positive, you have that little bit, confident. Oh, okay. At least I got the sign right. So I'm probably on the right track. So I end up at 100 meters. I start at 40. Okay. So I do. Yes, sir. Certainly. And that. All right. So back here, 60 seconds to 45, right? 60 seconds minus 45 seconds. So I end up with 60 meters, 15 seconds, 4.00 meters per second. Oh, I should have been boxing these, shouldn't I? So I know that that's, again, he's moving, the athlete's moving forward again, right? That's his velocity. Yep. And to make it clear this velocity, I should have been better and put positive on it. Because it could be interpreted speed without that sign on it. Correct. Per time. It's the rate that position changes. Change of position is just your displacement. But velocity is the rate that changes position. Okay? And that's why it has the time on the bottom. He wasn't. He just stopped. So he ran forward for 60, stood there, then moved back somewhat, and then ran forward to the end. Yeah. Kind of a weird thing, you know, but training, that's what it is. Training. Not a race. I hope not a race. All right, on to part B here. Part B. In part B, let's see, what is the magnitude and direction of the athlete's average velocity over the entire 60-second interval? So they're asking what the average slope is. And there's two ways we could do this. We could say, okay, I'm going to take what's called a weighted average, because all of these, all the individual parts, the four individual parts, contribute to the average slope, but they contribute based on the amount of time that they happen. So, like if A contributes one part, B contributes 2 parts, C 1.5 parts, D 1.5 parts. And if you're going to remember back to chemistry, doing isotopes, you maybe did some weighted averages. I don't choose to do it that way. I choose to say, okay, the way I think about average velocity is, if I continued, if I went at the average velocity, I'd get to the same place in the same amount of time, but I'd do it in one motion rather than multiple motions. What would a graph look like for a single motion to get to 100 meters in 60 seconds? What would tell me that I'm at a constant velocity? What type of line? It's a straight line. So if I do a straight line from here right to here, so from the beginning to the end, that would represent me doing the same trip but at an average velocity. So I'm going to approach it the exact same way. All right? And to show average, we put a straight line over it, no hook on the end. That means average. Okay? Now I'll bring this a little higher up so you can see better. I end up at 100 meters. I started at 0 meters, and I ended up at 60 seconds, and I started at 0 seconds. So I get 100 over 60, which is 1.67 meters per second. On is positive, so I end up, it's down the track. My average velocity is 1.67 meters per second down the track. Yes?